An important concept in both mathematics and its applications is to determine when a function is getting bigger or smaller. The technical definition is to say that a function is non-decreasing on an interval I if whenever x is less than y, then f of x is less than or equal to f of y, and strictly increasing if that inequality becomes strict, that is, f of x is strictly less than f of y. Graphically, this is fairly intuitive. Strictly increasing functions are getting bigger as our values get bigger. Non-decreasing functions are the same, except they're allowed to flatten out as long as they don't go downwards. The flip side to this is decreasing functions. A function is non-increasing if whenever x is less than y, then f of x is greater than or equal to f of y, and strictly decreasing if f of x is strictly bigger than f of y. The same story holds graphically. Strictly decreasing functions are always getting smaller, with non-increasing functions allowed to flatten out so long as they don't get any bigger. Now, nothing here mentions derivatives or differentiability, and indeed, increasing functions don't have to be differentiable. However, if our function is differentiable, we expect the derivative to say something about increasing or decreasing. That's because the derivative measures the instantaneous rate of change. So if the derivative is positive, our function is getting bigger, and hence a positive derivative should correspond to an increasing function. And vice versa, a negative derivative should correspond to a decreasing function. This turns out to be true per the following theorem. If f is differentiable on the interval I, then if the derivative is greater than or equal to 0 for all x in I, f is non-decreasing on I. If the derivative is strictly positive, then the function is in turn strictly increasing. And you can imagine that the dual notions hold for negative derivatives and decreasing functions, with strictly decreasing corresponding to strictness of the inequality. This suggests to us the following strategy. Let's find where the derivative is equal to 0 or does not exist, since these are the only places where the sign of f could possibly change. Between these points, the sign of f prime must remain constant, so we can then determine whether f is increasing or decreasing by checking the sign of f prime on the intervals created by these points. These points are thus so important that they warrant their own definition. Any point where the derivative is equal to 0 or does not exist is said to be a critical point of f. Alright, so let's put this to work. Let's find the intervals of increasing and decreasing for the function x over x squared plus 1. To find the critical points, we need the derivative of f, which ends up being a quick application of the quotient rule. Now this exists for any x, so we're going to look for those points where the derivative is equal to 0. This in turn corresponds to those points where the numerator is equal to 0, which give us x is plus or minus 1. Using these points to cut the real numbers up into intervals, we want to find the sign of f prime on each of these intervals. I like to express this as a table, but you can do it some other way. And we can find the sign just by plugging any point in each of these intervals into f prime. If we do that, we get the following. From this table and our theorem, we can thus conclude that f is strictly increasing on the interval -1 to 1, and strictly decreasing when x is less than 1 and x is greater than 1. Thus, we can use first derivative information to decipher when a function is increasing and decreasing.